Right. So before we start, let me ask you, do you have any question that you want to discuss? If there are no question, then we can start. So let me start with the definition that I gave last time about projection. So there was an error in that definition. So let me start with the correct formulation for the projection. So uh, yeah, last time we saw that projection, one can project a vector, projection of a vector on a vector. All right. In a So I'm working with the inner product space V. Okay. So projection of a vector V in V on a vector W in V. All right. So situation you may think of like this. This is vector V. This is vector W, and you want to project it on this, so that the point, the head of the uh, vector V is at the shorter distance from this vector W. Okay. In particular, it is it is in the shorter distance from the line that it spans, the line W spans. All right, makes sense. So this projection of the V in the direction of W is inner product of V with W divided by the norm of W square times W. So last time when I discussed, I didn't put a square on top of the magnitude of vector W. Okay, on the mod of W. So this is the correct formulation, and you can generalize this formulation to projection of a vector onto a vector subspace as well. All right. So now, in case if W in V is an orthogonal, no, sorry, it's an orthonormal vector. So that means what? Because it's an orthonormal, the norm of W is 1, right? So in that case, the projection of V in the direction of W just become this. Okay. So this is in the case of orthonormal vector, if you're projecting a vector in the direction of orthonormal vector, and for a vector subspace, so projection of a vector
Sir, please scroll little down.
right?
Sir, sir, little more. Sir, start. Yes. Okay, sir. Thank you.
Uh, so if you want to project a vector in V to a subspace in subspace W of V. All right. Uh, and suppose, okay. So suppose that these vector v1 to vk is orthonormal basis of W, then one can define the projection of V uh, onto W to be the summation of the projection of V in the direction of each VI, where I is varying from 1 to k. And now, what is the formula that we discussed for the orthonormal basis? A projection in the orthonormal basis, you can replace that down. So it is going to be V1, V in a product with Vi in the direction of Vi. I is varying from 1 to k. The summation is varying from 1 to k. So this will be the, if you have a vector subspace you want to project on. All right. So now in case, suppose, now suppose this case, uh, suppose you have given a set of vectors v1 up to vk, okay, or let me take three vectors. Suppose v1, v2, v3 is a is an orthogonal set in some vector space V. Then for any V in V, how does the projection of V look like on the span of these three vectors? So the projection of V on the span of these three vectors is going to be just the sum of the projection on the individual vector. All right. V1 projection of V onto V2, projection of V onto V3. All right. Now we have given that these are orthogonal vectors. They are not orthonormal vectors, right? So first we can convert each of this Vi into orthonormal, or you can use this formulation that I gave earlier for any general vector. You just need to divide by the magnitude, the square of the. So so you can either convert it into orthonormal orthonormal subset. That means converting your V1, V2, V3, an orthogonal set to V1 divided by norm of V1, V2 divided by norm of V2, V3 divided by norm of V3, a orthonormal set. All right. And apply this formula. So it will be just, so then the projection of V will be just V1, sorry, V with V1 divided by norm of V1 into V divided by norm of V1 plus the second term plus the third term. So, but it is again, it is same. You can take the this norm outside and this will again becomes this thing, nothing but divided by norm of V1 square. And that's it. Okay. So So this is what the projection that we discussed last time. So uh, let me discuss it by an example. Okay, that would be easier for you all to understand it better. All right. So now let's take this example. So you have given a set A of vectors. Yes, you have given this set of vectors. Let's just take two vectors from that. Okay, so you have given a set of vectors of two vectors in R3. Okay, with the usual dot product. All right. Now you have given another vector, which is, let's say, this v is equal to this, and you want to find out so projection of v onto the span of A. What is this one? Okay. Now how do we do that? So first of all, these vectors, what is the norm of this vector? So in order to check that whether they are orthonormal or not. So are these vectors? So let me first name these vectors. Let's say call them v1 and v2. So let v1 is equal to 1, 2, 3, and v2 is equal to 0, 1, 2. So what is the norm of v1?
13. Root 13.
Root 13. So it is 1 plus 4 plus 9. It is root 14, right?
Yes, yes, yes. So that's fine. Yeah.
Yeah. And now what is the norm of v2? Norm of v2 is 0 plus 1
5.
plus 4
Root 5.
root 5. Correct. Right. So they are not orthonormal, right? They are not orthonormal uh, basis. Are they orthogonal? Okay.
No, they are
So
not.
they are not orthogonal as well. So they are just random vectors. So if you have just random vectors, you want to uh, uh, find out the projection uh, of these vectors onto, yeah, unit. Uh, yes, you need to start with an orthogonal subset of the vector. So first, we need to convert this A into an orthonormal uh, or orthogonal set, right? And then we will project it onto, and then we will project, and then we will find out projection of W onto the span of this. So converting a random set of vectors, not random set. So you can check that they are linearly independent. Okay, so they are linearly independent. They are not dependent. So they are linearly independent. So converting a linearly independent set to orthogonal set or orthonormal set is what we are going to discuss today, which is called the Gram-Schmidt procedure. Okay. And then once you have that, you can find out the projection of this on a random set. So we will discuss this later. So let me first start with an example uh, where you have already given an orthogonal set. So let's take another example of A, which is 0, 1, 0, 4, 0, and it will be easier as well. 1, 0, 2. So clearly, this is a linear dependent set. It's linearly independent, as well as, is it orthogonal?
Yes, it is.
It is orthogonal also, it is independent. And now I want to project the same vector that I had earlier, which was 0, 0, 1. Uh, so again, the question is same, projection of V onto the span of A. All right. So how do we do that? So we can first, so we have given two vectors. Let me call them, let V1 be 0, 4, 0 and V2 be 1, 0, 2. So projection of V in the direction of V1 plus projection of V in the direction of V2, right? So now you take, what is the projection of V in the direction of V1? So you need to first have the inner product, the vector V1 divided by the norm of V1 square plus inner product of V with V2, V2 vector, norm of V2, right? Now what is norm of V with V1?
It's 0. I mean,
Right.
VV1 inner product is 1. 0. Yeah.
Yes, it is 0. Similarly, what is V and V2? V with V2?
It's, a, it's 2.
Yeah, it is 2. And V2 is 1, 0, 2. And the norm is, what is the norm? Norm of V2 is 1 plus 4, root 5. So the projection is, this is the projection of vector V in the span of uh, this of these two vectors. Okay. So this is how we calculate. And in case you have orthonormal, so you don't have to worry about these. You don't have to worry about the norms because then these norms will be 1 if you have given an orthonormal set of vectors. All right. Does it make sense? Good. So let me discuss one more example. Uh, so in the last session, I don't know whether you guys remember or not. I gave you an exercise which one of you already solved during the session. Oh, right. Sorry. Yeah, it should be 5 because I'm taking the square. Thank you. Thank you. It is 2 by 5, 4 by. You are correct because I'm taking the square. All right. So last time I gave uh, inner product structure on this space of polynomials, right? And I call that to be P2X, which is defined to be where A0, A1, A2 are real number. And the exercise was to say that given two polynomial, which is A0, A1x, A2x square, B0, B1x, B2x square, given these two polynomial, I define the uh, uh, inner product to be the integration from 0 to 1 of the product of these two polynomials. Okay. And I don't know whether you guys have figured it out or not, but it is simple. It is an inner product. So P2 X with this, I call that to be this type of inner product. This is an inner product space, inner product space. Now, in this inner product space, uh, we saw that set of these vector 1, x and x square, this subset of uh, vectors are not orthogonal subset. So this subset is not an orthogonal subset. All right. Why? Can anyone tell me quickly why they are not orthogonal to each other? What is the inner product of so for orthogonality, you need to check that their mutual inner product should be equal to 0, right? So what is the inner product of 1 and x according to this definition?
So it's all the inner products are mutually zero here because the coefficient of one is not equal to coefficient of x. So the coefficients differ, so it would anyway be zero.
No, but we are doing a product here. Look at the inner product definition of the inner product. This is the inner product. I'm taking the product of these two things. So 1 and x, if I take the product of 1 and x, what it would be? It would be x, right?
Yes, it should be x dx. Yes.
So is it 0? Integration of x, is it 0? It's not.
It's half.
Yeah. So it is not 0. Similarly, x and x square, this inner product, is also not 0 because it is going to be x cube, which is not 0. And similarly, inner product and x square and 1 is also not 0 because it is going to be integration of x square. All right. So they are not an orthogonal set. Similarly, their norm of each of the vector is not 1, except I guess the first one. So what is the norm of the first? Just a single one. It is dx. So it is 1. Right. Except that if you take if you calculate the norm of any other vector, so norm of x, let's say, norm of x is equal to the inner product of x with itself. Now, what does it mean? It means that x multiplied with x, it is x squared dx. So it is going to be 1. First of all, it is going to be x cubed by 3. That's the integration, 0 to 1. If you solve that limit, you will get 1 by 3. All right. And similarly, x square, you can also calculate that as well. It is going to be x to the power 5 by 5, 0 to 1. It is going to be 1 by 5. All right. So they are not unit vectors as well as they are not orthogonal to each other mutually. Now, what is the projection of x onto this vector 1? So this is what the question is. Projection of x and similarly projection of x square onto 1. So how do we calculate the projections? Just need to use the formula. So how do we calculate the projection of x onto 1? It is
Inner product of x
inner
dot
product.
1 and x.
It is inner product of 1 and x in the direction of 1 divided by norm of square, right? Now, what is norm of 1? Norm of 1 is
1 itself.
1, right? So it is going to be 1 inner product of 1 with x, which we calculated here. It is 0 to 1 integration of x dx. which is going to be 1 by 2, which is going to be x square by 2, 0 to 1, which is going to be 1 by 2. All right. Is everyone fine with this? Any doubt in the projection, in the first projection? So I have projected my vector x. Okay. So x is a vector in this space. Okay, you need to get comfortable with that thing. So x is a vector in this space, and you are projecting your x into the vector onto the vector y. Okay, so it is half. Similarly, if you project uh, if you want to project your vector x square onto 1, what would it be? It would be 1 x square 1 in the direction of 1 divided by norm of 1 square. Again, norm of 1 square is this is 1, and this x square in a product of x square with 1 is x square dx, which is going to be x cubed by 3, which is going to be 1 by 3. So this is what the projection is going to be. So it might seem complicated, but because of this inner product structure, they have the product in the product structure in terms of the uh, integration. But uh, I think this example is useful to make you understand what is going on. Okay, so now here I discuss one thing. Let me come back to this thing. So in this, before discussing this example, I mentioned this example of two vectors which span a subspace in R3, but they are not orthogonal to each other. So I cannot project my vector onto this subspace. In order to project these vector onto the span of these two vectors, I need to have an orthogonal set of vectors or orthonormal subset of it. X is in norm of x times 1 by root 3 in this example. Uh, which one? Uh, Let me number them so it will be easier for you to tell me. Okay, I would like to be number 1. This is number 2. This is number 3. So which one you are saying? Norm of x equation. Norm of x. Okay, okay. No, it is 1 by 3, right? Look at this. Uh, norm of x. Norm of x is equal to norm of inner product of x with itself. Now this inner product is what? It is integration of 0 to 1 x multiplied with x, which is x square dx. Now what is the integration of x square? It is x cubed by 3, and if you take the limits, you will get 1 by 3. So it is 1 by 3. It's not square root of 1 by 3. Right. So yeah, what I was talking about this. Yeah. So if you have a vector that you want to project onto a subspace, so for that you need to have orthogonal basis of that subspace. And how to obtain that orthogonal basis or orthonormal basis of that subspace, there is a process that I'm going to talk about, which is called Gram-Schmidt procedure. All right. So let me start with that Gram-Schmidt procedure.
Sir,
Yeah.
in example 3, you have mentioned it is orthogonal, sir. It is not orthogonal.
All right. So thanks. This is not an orthogonal subset. Right. Thank you. Thank you. Uh, yeah. So let me talk about the Gram-Schmidt process. All right. So suppose you have given a linear dependent vectors. Okay. So suppose, so let me take that example itself and explain the process in this example, and then we will talk. And then I will give the general description. So let me copy this from here and paste it over there. Right. Okay. So in this example one, we had this set of vectors 1, 2, 3 and 0, 1, 2 in R3 with dot product. And I want to project this onto the span of A. All right. Project this onto the span of this, right? And let me call these vector to be that. And we have noticed that these vectors are not orthonormal. So note V1, V2, note subset A is not an orthogonal subset or orthonormal subset of R3. All right. So this is what we have noticed. So now I want to convert this uh, subset into an orthogonal set, but we have noticed that they are linearly independent subset. So how do we do that? So we start with, so we have V1, V2 in R3 dot product. So I take, yeah, so I start with my E1 to be just V1 itself. Okay. And further, what I will do, I will consider W1, which is going to be E1 divided by norm of E1. Okay. So here I'm constructing the orthogonal subset. Here, orthonormal subset. Okay. So for the first step, very first step itself is just you take your E1 to be just V1 itself. Okay. For orthogonal. And for orthonormal, you need to divide it, you need to have it unit length. So you divide it by its norm. Okay. Now for V2, for E2, sorry, we need to subtract the projection of, you need to subtract the projection of V1, projection of V2 in the direction of V1. All right, in order to make it orthogonal. And in order to make it orthonormal, what we will do, we will again take E2 divided by norm of E2. All right, does it make sense to all of you? Okay, now let's see. So my V1 was, V1 was 1, 2, 3, right? V1 was just 1, 2, 3, and V2 was 0, 1, 2. So I need to find out. So E1 is just 1, 2, 3. Now what is W1? W1 is 1, 2, 3 divided by the norm of 1, 2, 3, which is 1 plus 4 plus 9, which is going to be 1 by 14, 2 by square root 14, 3 by square root 14. All right. Now what is E2? For E2, we need to first, so E2 is 1, 2, 3, sorry, 0, 1, 2. That is my V2. Now what is projection of V1 into V2? So projection of 1, 2, 3 onto V2. It is 1, 2, 2, 0, 1, 2. Now projection of this, you need to take inner product of 0, 1, 2 with 1, 2, 3 in the direction of 1, 2, 3, and then divide by the norm square. All right. All right. Now, what is this inner product? It is dot product only because we are working with R3. It is dot product, R3 with dot product. So, what is this dot product? Can anyone tell me?
8.
Right. 2 plus 6, so it is 8. Divided by this norm is 14. Right. 1, 2, 3. Right. So, it is going to be 7, 4 by 7. Or if when after doing this subtraction, we will get 4 by 7. What do we get? We get 4 by 7. 1 minus 8 by 7. 1 minus 8 by 7. 2 by 2 minus 12 by 7. Right. Now what is this? 1 by 7, 4 by 7 minus 1 by 7 minus, yeah, is this fine? Now for W2, we need to divide by the norm of E2. So my E2 is minus 4 by 7 minus 1 by 7, 2 by 7, and I need to divide by. So I can just take 1 by 7. All right. And this is my vector minus 1, minus 2, minus 4, minus 2. Divided by be taking the square and square root, so which is going to be 16 by 7 square, 1 by 7 square, 4 by 7 square. You can take 1 by 7 out here as well. So 1 by 7 gets cancelled, and you will get 16 plus 21, 21 square root of 21. So it is 1 by square root of 21. All right. Now, what you can do, so now you have converted, you have converted your A, which is V1, V2, a linear independent set, into an orthogonal subset, which is uh, 1 to 3 and 1 by 7 minus 4 minus 1, 2, and then orthonormal subset, which is um, yeah, 1 by square root 14, 1, 2, 3, and 1 by square root 21 minus 4 minus 1, 2. All right. Now you can check. You can check that this is orthogonal. Okay. So can anyone tell me quickly that why it is it orthogonal or not? Is it orthogonal? Is this subset? This subset. Good. And similarly, you can check that this other set is also orthonormal. Okay. Uh, yeah. So this is how you obtain orthogonal as well and orthonormal also. For orthonormality, you just need to divide it by the norm of the vector again. For orthogonality, you need to subtract the projection of the vector. And remember the formula for projection because my vectors are here orthogonal. So you need to divide by the square. You cannot take away the square because, uh, yeah, otherwise this formula will be wrong. So you need to keep that in mind. Okay. All right. So now let's work with another example. Um, let's call that example 4. You have this subset given by, again, the similar vectors. I will just add one more vector to it. Okay. In R3. Okay. So first check that is a linear independent set. Is A linear independent set?
It's linearly dependent.
Dependent? Okay. Can you tell me the relation with
Yeah,
that's
V1
dependent on
minus
what?
V2. So V3 is equal to V2 minus V1 minus V2.
V3 is equal to V2 minus V1.
No, V1 minus V2.
Okay. 1, 2, 3 minus 0, 1, 2. If you subtract that, you will get 1, 1, 1.
Oh, it's sorry, one.
But
Okay, okay. Yeah.
yeah, V3 is 0, 1, 1, right?
Ah, yes,
So
yes.
what is the, yeah, what's the way to check a linear dependency when you have the matching number of dimension
Okay, we can
of the
go
space?
through determinant. Determinant.
Yeah, so why didn't you calculate the determinant? So determinant is quicker way, right? So if you calculate the determinant, you will find out that it is non-zero. Now, what's the determinant of this?
-1, sir.
Minus one, right? So it is non-zero, clearly. So it is a linear independent set. So it is A is linearly independent. All right. So it is a linear independent set. Now I want to convert it into a linear orthogonal as well as orthonormal set. Okay. So we have already calculated. We have already proceeded with few steps. Okay. We have already converted a subset of this set into an orthogonal and orthonormal subset. Now let's keep on doing this. Okay. So I want to find out the third vector. Okay. Now I want to convert the third vector also into an orthogonal into a vector so that it becomes orthogonal to the rest of the vectors as well as its norm is also equal to 1 in the orthonormal subset. Okay. Does it make sense? What I'm saying, trying to do, right? So for that, what do we need to do? So notice here, in order to make vector v2 orthogonal to v1, what we did, we removed the projection of v1 in the direction of v2, right? To convert v2 into an orthogonal subset, I removed the projection of v2 in the direction of v1, right? Now, if I want to make e3, okay, orthogonal to v1 as well as v2, so what do I need to do? Can anyone tell me?
Remove
Based on
both the
this,
projections.
yeah, remove the projection of v3 in the direction of v1 as well as in the direction of v2, right? Correct. Nice. So let's do that. Uh, so my e3 because I've already calculated E1, E2, so I don't need to calculate E1, E2 again. My first two vectors are same. So E3 is what? V3 minus projection of V1, projection of V3 in the direction of V1 minus projection of V3 in the direction of V2. All right. And my W3 will be just E3 divided by norm of E3. Okay. So it makes sense. Is it any doubt here? No, right? Okay. So now let's calculate each of this one by one. Okay. So let's calculate one by one. So first, let me start with calculating projection of V3 in the direction of V1. Now, what is this? It is V3 V1 dot product divided by norm of V1 square times V1. Now, what is this? Can anyone quickly compute the dot product and the norm divided by the norm?
So the dot product is 5
Dot product is 5. Okay, good.
and the norm is root 14, so it becomes 14.
Yeah, it is 14. Right. And it is V1 is 1, 2, 3. So you just need to multiply. So just keep the integer outlets for a bit. Okay, and now what is the projection of V2, V3 in the direction of V2? So again, you need to calculate V2, V1, sorry, V3, V2, and divide by the norm of V2 in the direction of V2. So again, can anyone quickly tell me uh, dot product of V2, V2, V3?
It's 3.
3 divided by the norm of V2, which is root 5, right? So it is 5, 0, 1, 2, right? Now you need to just put everything back into this formula. So E3 is V3 minus this vector and V2. So V3 was 0, 1, 1 minus 5 by 4, 1, 2, 3 minus 3 by 5, uh, 0, 1, 2.
That will be 5 by
What
14.
is this? Sorry, 5 by 4. Right. Now, can anyone tell me what is the answer at the end? Okay. Uh, yeah. Has anyone solved it before me? Can tell me the answer. 17 minus, we can simplify this. 5 by 7, 25, 7, 25, right. Uh, 7, 21, 1. It's going to be- Right. Thanks. Thanks, Amrit, for helping me out. 5 minus 5 by 14 divided by minus 11 by 35 Um, all right, so you can do this computation. So, and then once you get this, I am believing this doesn't look right to me because it is minus minus, so it will add up and then we are subtracting 7. So it should be uh, 25, it is 46 minus 7, 13. Right. I don't know about this thing, uh, but I'm believing Amrit on this. And then once you get this E3, you just need to divide it by the norm of this. So now you understood the practice, you understood the procedure, okay? How does it work? So you need to start with the, you need to have a linear independent subset or set that you want to convert into an orthogonal orthonormal set. And the process is simple. Okay. So let me now write in the case, in the general case. All right. So the GS procedure, suppose V1 to Vk is a linear independent set of vectors in V, then let E1 to be V1 and W1 to be E1 by norm of E1. Okay. And for J varying from 2 to K, do this, define Ej. Now Ej is converting your Bjth vector into the orthogonal or orthonormal vector. So you need to you need to remove the projection of all the vectors that you obtained before Ej. All right. So Vj minus removing the projection of V1, sorry, uh, projection of V1 in the direction of V1, projection of Vj in the direction of V2, projection of up all the vectors up to Vj minus 1. All right. It makes sense. So you have to remove all these projections and you define Wj to be the Ej divided by the norm of Pj. All right. So then uh, E1 up to Ek denote is an orthogonal subset, and W1 to Wk is an orthonormal subset. All right. Any question on this? All right. So now here, let me state a few facts uh, which are clearly visible. Because you have noticed that the way I have obtained E2 or E1. So E1 is just V1 itself. E2 is a linear multiple it is a linear combination of V2 and V1, right? You can clearly see that E2 is linear combination of V2 and V1 because projection of V2 is in the direction of V1. So it is a linear combination of V2 and V1. So the span of EIs is a subset of VI, is a subset of span of VIs. All right. So it is clear that span of E1 EIs, E1 up to EK, is a subset of span of V1 up to VK. All right. But uh, because E1 up to EK is a linear independent set. Why it is a linear independent set? Because it is uh, an orthogonal subset, right? And orthogonal subsets are linear independent. And also you can notice that it is minimal span for this space because the minimal because V1 up to VK, it is a linear independent set with only k vectors. So EK also has k vectors. So E1 to EK are also orthonormal basis for this span. So you will get now since E1 up to EK is an orthonormal subset, we get that span of E1 up to EK contained span of E1 up to EK, right? So by these two equations, they contain each other. That means they are equal. So span of E1 up to EK is equal to span of V1 up to VK. Okay, this is one fact which is easily noticeable. Uh, Now another fact is that every finite dimensional inner product space has an orthonormal basis. So we already know how to find out a basis to a set to a vector space, and once you have a basis to a vector space, you can convert that into an orthonormal basis using this Gram-Schmidt process. So this is also direct. All right. Uh, yeah. Okay. So now, uh, do you guys have any question on this GS procedure? If not, then we can move to orthogonal transformations.
Sir, what is the last
Yeah.
line? Can you please repeat it, sir? As an ortho.
Yeah. Every finite dimensional inner product space has an orthonormal basis too. And why do I say that? Because if you have a finite dimensional vector space, you have a basis to that vector space, right? Now, using that basis, you can apply this Gram-Schmidt process to convert that basis into an orthonormal basis. All right. So we start with a linear dependent sets. In that case, you will start with that basis, and then you will convert it into an orthonormal basis, W1 to WK. Okay, that makes sense.
Yes, sir.
All right. Any other question before we move on to orthogonal transformations? All right. Now let's talk about orthogonal transformations. So, before we talk about orthogonal transformation, let me start with an example again. So, we have all seen what are linear maps, right? And we have also seen that how to associate a matrix to a linear map, right? So let's talk about uh, another linear map, a simpler one, which is from R2 to R2, and you have already seen this linear map. So example number 6, I guess, if I'm counting it right. So consider this linear transformation from R2 to R2. Okay, and this is defined by this way that 1 comma 0, and this is defined by sending the basis 1 comma 0 to 0 comma 1, and another basis 0 comma 1 to minus 1 comma 0. All right. So what I'm doing, I'm sending 1 comma 0 to 0 comma 1 and 0 comma 1 to minus 1 comma 0. If I try to see this in a picture, what I'm doing is, suppose this is my y axis, this is x axis, and this is 1 comma 0 vector, and this is 0 comma 1 vector. All right. Now what I'm doing is, I'm sending 1 comma 0 vector, 1 comma 0 vector. So let me draw another picture. This is x, this is y, this is my linear transformation T. So what I'm doing is, I'm sending T of 0 comma 1 to this vector, which is E2, right? And T of 0 comma 1, sorry, T of 1 comma 0 to E2, and T of 0 comma 1 to minus E1. All right. So do you see, if you travel from 1 comma 0 to 0 comma 1, what do you see? That if you travel from 1 comma 0 to 0 comma 1, now you are traveling from y axis to the x axis. So there is some kind of a shift has happened. All right. So earlier you were traveling from x axis to y, and now you are traveling from y to x. So there is some kind of a shift has happened. So you may think of that you have rotated. Everything has been rotated. Okay, now your x-axis has become the y-axis, and your y-axis has become the minus x-axis. So you have rotated your plane by how much of degree? Can you guess?
By 90 degrees.
Yeah, that is correct. So we have rotated our plane by 90 degrees. Okay, so that is what this map is doing. Okay, now let's try to, so this was the geometric interpretation of this map. Now let me come back to by what does this map actually does. So, so what is the expression of t x comma y? Can you guys tell me? What is t x y? T of x y is uh, x of 1 comma 0 plus y of 0 comma 1. Now, can anyone tell me, now use the linearity property of t, and
X times 0 comma 1 plus y times minus 1 comma 0.
yeah, and what does that give you? What is the final answer? It is going to be minus y comma x. Okay. Uh, yeah. So this is what this map is: xy going to minus minus y comma x. Now, uh, now on both ends, we have inner product to be given by dot product. All right. So let's see. So what is the norm on the right hand side? So first check the length. So what is the norm of a vector x comma y on the right hand side in the domain? It is x square plus y square, square root of this thing. Now, what about the length of its image? What is the length of txy? It is
The
equal to the
same.
length of,
It's the
yeah.
same thing.
So this is same, right? And what about the inner product? Inner product between two vectors. So let's say you have x1 y1 and you have x2 y2. Now what is the inner product? It is x1 x2 plus y1 y2, right? Now if you take the images of these vectors under T and find out their inner product, what it would be? It is minus y1 x1 minus y2 x2. Now what is the inner product of this?
Same thing.
Same thing, right? So what you have noticed that, and you can also calculate the angle as well. What is the angle? Angle is cos inverse of the inner product of vectors divided by norm of the vectors, multiplication of the individual norm of the vectors. Now we have already seen because the inner product is same and their norms are also same, so their angles are also same. So what we have seen that this space, this map, what it does, it preserves the length. Okay, so the length of the vectors is preserved because image and the actual vector has the same length. So the image, the length is preserved, the inner product is preserved, and the angles are also preserved. Okay, so these type of transformations, linear transformations, which preserves length and angle, are called orthogonal transformations. Okay, so linear maps that preserve length and angle, okay, are called orthogonal transformations. All right. Now, in all these three things, in the length, in the inner product, and the angle, what you guys have noticed that we are only looking at the inner product of two vectors. For example, in length, we are only looking at the inner product of the vectors inner product with itself. In case of angle, you need to know the whether it preserves the inner product with other vectors or not. All right. So it is sufficient to just say that if it preserves the inner product, then it is a then it will preserve the length as well as the angle. All right. So mathematically, the definition goes as follow that linear transformation T from vector space V to W is said to be orthogonal transformation if uh, VW, inner product of VW, is same as inner product of TVW. So one thing to notice here that on the right hand side, on the right hand side, you are applying the inner product of V. On the left hand side, you are applying the inner product of W because the elements are in W. Okay, so let me use a better notation. Uh, yeah. So let me take V1, V2, V1, V2. That's for all V1, V2 in V. All right. So, so here is one example that you have seen that xy going to uh, minus yx, and you have noticed that it is a 90-degree a rotation, right? Now, instead of 90 degree, if I just want to rotate my plane by some theta angle, so what would be the expression? Okay, so let's see that. So I'm calling this map rotation by theta angle, rotation of a plane by a theta of xy plane by a theta angle. All right. So I will just directly write down the map. I won't get into detail how do we get that. But if you ask me, I will let you know. It is this map is defined to be 10 goes to cos theta sin theta, 01 goes to minus sin theta cos theta. All right. So this is how we define the map. The basis goes to these bases. And now, uh, again, my same question: what will be the image of xy? Can anyone tell me? What will be the image of xy?
So we can write that as t of x times 1 comma 0, which will go to x times cos
Right.
theta sin theta, and
Right.
plus minus sin theta cos theta times 0 1.
Right. So what will that give you?
That will be giving me cos theta minus sin theta and minus sin theta cos theta xy. Will the
So
transformation will be, yeah.
is this the correct one? Is it correct?
Yes.
Right. Okay, good. Um, so this is the
Uh,
transformation. Hmm. Any doubt?
no, sir.
Good. So this is the transformation. This is how it will look like. All right. And this matrix is known as the rotation matrix. Okay, sorry. This transformation is called as the rotation transformation of the xy plane. And as well as you can write down the matrix using this. What will the matrix? Matrix is the
Cos
images
theta sin
becomes
theta
columns,
minus sin theta cos
right?
theta.
Images becomes the column, so it will be cos theta, sin theta, minus sin theta, cos theta, right? So this matrix is called the rotation matrix of xy plane. All right. Now, as we have noticed earlier, you can notice here as well that it preserves the ortho. It is an orthogon. It is an orthogonal transformation. Okay. So check that. Let's check. So what is yeah. So let's take x1, y1, x2, y2. Okay. Their inner product is simple: x1, x2, y1, y2. Now, what is the inner product of this? X cos x1 cos theta minus y1 sin theta, x1 sin theta plus y1 cos theta with the same thing: x2 cos theta minus y2 sin theta, hmm, x2 sin theta plus y2 cos theta. Correct? Now, what is this? What is this inner product? So we will first multiply this term with this term. All right. And then in the second coordinate, we are multiplying. Oh, sorry. summation with this thing. Right. All right. Now, if you multiply, what will you get? X1, x2 cos square theta uh, minus x1, y2 sin theta cos theta plus y1, y2 sin square theta plus minus x2, y1 sin theta cos theta. All right. And what about the second term? You can multiply that. What is the end result? So in the end, you will see that these terms will cancel out. So there will be similar terms here. Let me write it down. X1, x2 sine square theta, uh, x1, y2 sine theta cos theta, and then y1 cos theta, y1 x2 sine cos theta sine theta, plus y1 y2 cos square theta, right? Now y1 x1 y2, this cancels out with this, y1 x2, this cancels out with this. What is remaining is this x1 x square cos square theta plus sine square theta plus y1 y2 with the same thing. Now, uh, what is the value of cos square theta plus sine square theta? Anyone know this identity?
Yeah, so that will be the same as x1, x2 plus y1, y2, the usual dot product.
Yes. So the identity is that this is equal to 1. So the answer will be 6. So we have proved that it is an orthogonal transformation. So let me call this map to be T theta. T theta is an orthogonal transformation. All right. Okay. Now let's look at one more example, which is of the similar type. Um, defined by R2 to R3. It is given by xy. T of xy is equal to minus x minus xy 0. All right. Now, can anyone check that it is a orthogonal transformation? So I need to check x1 y1 dot product with x2 y2, which you already know, is equal to the t of x1 y1 t of x2 y2. On both sides, we have the standard dot product. So Yeah, T is orthogonal transformation.
Yes. Good. So what we have noticed here is uh, that orthogonal transformation need not to be between the same dimension spaces. Okay. So in this case, the dimension of domain is 2, dimension of codomain is 3. So orthogonal transformation need not to be of between the same dimension. I gave this example because earlier the example that I discussed were between the same dimension space. Okay. So orthogonal transformation need not to be of the same dimension. That transformation between the same dimension. That is one thing. The other thing is uh, that suppose V1 up to Vk. Okay, let's take this example only. So in example, yeah, in above examples, we had, right. So we were working with basis of domain. We were working with the orthonormal basis of domain, right? For example, in this case, it was 1, 0 and 0, 1. It is also orthonormal, right? In this case also, you can work with orthonormal basis, which is the standard ones. So we we were working with orthonormal basis of the domain. So their images, which was E1, T of E1, T of E2, they are also an orthonormal subset of the codomain. All right. For example, in this case, in the previous example 8, image of T10 and image of 0, 0, 1, image of 10 and image of 0, 1, they are going to be orthonormal to each other, and their set is whatever set they form will be an orthonormal subset. All right. So in the previous example 7, we had cos theta sin theta and the image of 0, 1 to be minus sin theta cos theta. So they were also orthonormal to each other. Why they are orthonormal? Because my linear transformation is a orthogonal transformation. So it preserves the length and preserves the inner product, right? So because 10, length of 10 is 1. So length of cos theta sin theta is also, it should be 1, right? No, it's not about the dimension. It's not about the dimension. I'm saying they are going to be orthonormal subset, not basis. Okay, there is a difference. I'm saying they are going to be orthonormal subset, not basis.
Okay, it's
Uh,
just that the vector is rotated by an angle theta. So the basis in some other basis. So the length remains the same of the vector, right?
that is true. That is true. But it is more general. So in this example, yeah, it is by theta. I'm doing this. I'm rotating by theta. But the main point is that what is if you want to find out that they are orthonormal. So what do you need to do? You need to check their inner product, right? And their inner product is equal to the inner product of E1, E2, right? Which is 0 because E1, E2 was an orthonormal basis. Similarly, if you want to check the length of image vectors, then it is same as length of E1, which is 1, or even in case of E2 also. All right. So images of orthonormal basis of the domain under a orthogonal transformation are going to be orthonormal subset of the codomain. Okay. So let me write it. Uh, Image of an orthonormal in particular image of an orthonormal subset under an orthogonal transformation is an orthonormal subset of W or of codomain. In this case, it is W. Okay. Is this fine? Does this make sense to all of you? What I've written, right? In other words, if you are, we have already seen that any finite dimensional vector space has an orthonormal basis. Okay, so you can express your linear transformation always in terms of orthonormal basis, right? So suppose V1 up to Vn is an orthonormal basis of V, and T from V to W is an orthogonal transformation, then first of all, T of V1 is an orthonormal subset of W. Second, T of V1 up to T of Vn uh, forms an orthonormal basis of range of T. All right. These are all very direct consequences, right? Uh, and the matrix corresponding to T, right? So which is going to be where the columns are going to be TV1 and TVN as orthogonal or orthonormal columns. All right. So are these three statements clear to all of you? So if I start with an orthogonal basis of B and only orthogonal transformation, then I will have these three equivalent conditions, you would say. What's the confusion? Can you, if you can. So you have started with an orthogonal basis, right? Their images are going to be an orthonormal subset of W, right? And if I restrict my map, if I just only look at the subspace of T, where if I just only look at the image of T, that means the range, that then that orthonormal subset will also become the spanning set. Then it will become also the orthonormal basis of that range. right? And in particular, if I just express the matrix corresponding to this linear transformation, that means it has orthonormal columns. Because each of that, what do we mean by orthonormal column? That columns are vectors. So these column vectors are orthonormal to each other. And that is because we are working with orthogonal transformation and we have started with orthonormal basis. That's all. There is nothing special that I have written. It is just all direct consequence of working with orthonormal basis and working with orthogonal transformation. Thanks. Good. Now let's now consider this case 4. Uh, Suppose dimension of W is same as dimension of V, and that take to be equal to n. So in that case, the matrix corresponding to these, in that case, in that case, A, the images of the vectors TV1 to TVN, they become the orthonormal basis of W. All right. Is there any condition that the dimension should be same for V for this? No, no. Now I'm writing for when they are equal to when they are same. Because in our case it could be they need not to be same. All right. But if they are same, then they become orthogonal basis of the W itself. Second uh, T is an isomorphism that is direct because it becomes their image is basis goes to basis, so it is an isomorphism. Third point is that the matrix corresponding to T is of n cross n order, and because I'm working with the orthonormal and has orthonormal columns, okay, orthonormal columns of order. What will be the order? Order will be n cross 1. N cross 1, right? So now, if I just, so if I have T, okay, let me call this to be some matrix A. So this matrix will satisfy the condition that A into A transpose is equal to identity map, as well as A transpose into A is also equal to identity map. Okay, now why is that? Let us first see that A into A transpose such that this equal to identity A transpose into this. So let me see. So what is A? A is basically TV1 up to TV n. All right. Now where each TVI is a column vector of order n cross 1. All right. So this is what this is. Now what is A transpose? A transpose will be when each column will become the row. Okay. So now TV1 transpose up to TVN transpose. This will be your A transpose. All right. Is everyone with me till this point? Now, if I do the multiplication, so A into A transpose is going to be TV1 up to TVN multiplication with TV1 transpose up to TVN transpose. And if you multiply, it is yeah. Okay. Right. Right. Okay. So there is yeah. So there is a little problem here. Till this point, it is all fine. Okay. So that this does not happen. Okay. Hmm. Now consider case 5. Suppose you are working with Rn. W and V are both Rn. Okay. So in that case, all the above, whatever I have written makes sense. And you can have the corresponding matrix A, which is given by T, which is the matrix is given by this, will satisfy this condition that I'm going to have. Okay. So this only makes sense when you are working with Rn and with the standard dot product. Okay. So uh, your domain is also Rn, your codomain is also Rn, then you can have this kind of identity. So now if you multiply TV with TV transpose, now this multiplication is, uh, it is the usual dot product. If you express this column and if you try to multiply each entry with this, you will see that this is going to be uh, yeah. So it is going to be so this is n cross n matrix, and this is also n cross n matrix. So the result should also be n cross n, right? So you will see that you are multiplying this with this, then you are multiplying TV1 with TV2 transpose, and so on. So all the other entries will be zero except the first one. Similarly, you will multiply TV2 with TV1 transpose, TV2 with TV2 transpose, and so on. So what you will get? You will get an identity matrix, and rest of the entries will be zero because uh, TVIs are orthogonal to each other. They are orthonormal. So if they get multiplied with each other, with to itself, you will get one. If they get multiplied to any other vector, you will get zero. Okay. So matrices of this kind, we define these matrices of special type. Uh, so in particular, if you have a orthogonal transformation from Rn to Rn, then they correspond to matrices which satisfy this identity, which is all right. So we call, or you can independently define these metrics as well. So now definition, a square matrix is called an orthogonal. A square matrix is called an orthogonal matrix if a square matrix A is called an orthogonal matrix if A into A transpose is equal to identity map, which is equal to A transpose into. All right. So whatever example that we saw today, uh, especially examples 7, 8, 9. So let me, because then there we were working with R2 with R2. So first example that you saw was, one of the first example was this theta rotation. Okay. This was corresponding to map between R2 to R2. This was example 6, I
I think
guess.
that the minus sine theta would be like plus sine theta, and the A22 would be minus sine theta here. I think cos theta sine theta minus sine theta cos theta would be the rotation
Let me
matrix.
check. Cos theta minus sine theta cos theta. That was the rotation, right? This is what the rotation matrix. That's what I've written. You see the top here. This is what I've written. Cos theta minus sine theta cos theta. So you can check that this is an orthogonal matrix. Okay. So what is the transpose of this? Transpose is going to be cos theta sine theta minus sine theta cos theta. Now, if you multiply, you will get cos square plus sine square, which is 1. And then you will get cos theta sine theta minus cos theta sine theta minus sine theta cos theta, which is 0, 0, and 1. Okay, similarly, you can check for the other identity as well. Another example of orthogonal transformation could be this, which is again I'm taking from the rotation matrix of R3, half 0, 1, 0, half. So check that this is also orthogonal transformation. Okay. So what is A transpose? A transpose is half 0 minus root 3 by 2, 0 root 3 by 2, right? And if you multiply A with A transpose, what will you get? Half uh, plus 3 by 2. No, this is this a is this a orthogonal transformation, orthogonal matrix? If I multiply this, this half 0 root 3 by 2, so it is half, half, it is 1 by 4 plus 3 by 4, right? And then this with this, 0, this with the other, it is minus 3 by 4 plus root 3 by 4, 0, and then it will be 1, it will be 0, 0, 0, 1. So it is really identity. You can check for the other identity as well. All right. So this is also an example of uh, identity matrix. Sorry, this is also an example of orthogonal transformation. In general, if you consider this example, which is a rotation rotation along rotation of R3, rotation along z-axis. Then you have linear transformation given by this cos theta, sin theta, sin theta, cos theta, 1, 0, 0, 0, 0. If you have rotation along y-axis, you place 0, 1, 0, 0, 0 in the second column and second row, and rest will be your rotation matrix of. And similarly for x-axis, rotation along x-axis, uh, formula is this. So these are all linear transformations, orthogonal transformations, and their corresponding matrices are orthogonal matrices. All right. Okay. So exercise. So the exercise is, so earlier I talked about this projection map. Sorry, what I'm saying. So earlier I talked about this vector space of polynomials, right? With the integration as the inner product over them. And I discussed one linear dependent set, which is 1 x square and x. A is given to be this is a linear dependent set. So find out the orthogonal uh, basis of P2 and orthonormal basis of P2. Okay. So yeah, this is an exercise. Uh, and so how do we find out this? First of all, what procedure do we use? We have discussed this procedure
The
today.
Gram-Schmidt, the Gram-Schmidt.
Gram-Schmidt process, right? And you just need to plug in the values. You know the integration. You know the inner product. What's the inner product? You know that this is an independent set. You need to find out the projection of each vector with respect to the other. If you go through this note, some of the projections we have already solved. And then after doing that, you need to subtract them from this from the vector, and then you will get the orthogonal basis. And once you get the orthogonal basis, you then need to divide each vector by its norm to get orthonormal basis. All right. So yeah. So any question on today's topic, today's discussion, then you can ask me.
Sir, I have a doubt. Like, it is not based on today's discussion, but
Right. Right.
in okay.
Sir, week 8 is over, sir.
Week 8 is over. Yeah, this is the last session of week 8.
Sir, all topics are covered, sir, so far in week 8.
Right. All topics are covered. Yeah. Projections, Gram-Schmidt process, orthogonality, orthogonal transformations, orthogonal matrices. Last week we had inner product spaces. Yeah, so everything is covered. Last topic was orthogonal matrix. We have covered that. This was the orthogonal matrix. Right. Yeah, you had question, Greece. You were asking something and then you
Yeah.
stopped.
like in the graded assignment for week 8, like I could see two assignments for me. So like one is actually based on week 8 and the other one is week 9, but it is also given as part of week 8.
Is it? Okay, I need to check that. I don't know.
Okay.
Let me check once.
Yeah, sure.
Yes, sir.
Um,
Same assignment are given also in week 9.
oh, okay. Same assignment is given.
Like the graded
Graded assignment.
assignment for week 9 is also mentioned to be graded assignment week 8 under week 8, and week 8 also has its own graded.
Oh, okay, okay. So there might be some technical glitch. So you do the graded assignment of week 8 only. Okay, and I will ask.
Sir,
I am not.
sir, sir, the last date for week 8
Okay.
graded assignment is given as 8/8, sir. August 8.
That is actually week
Wait.
9 content. The If you look at the week 8, it will
Yeah,
be
yeah.
27.
So the first one is week 8. Yeah. So you correctly pointed out. Thank you, Grish. So week 8 assignment is the one that you need to submit by 30th of July. Okay. The another assignment that you see on week 8 page, which is graded assignment week 8, and the deadline is 8th August. That is the calculus part, which you have not seen. Right. So you can't solve that. So don't worry about that. Don't submit that. I will ask them. There is some technical glitch. It is a week 9 assignment, so you don't worry about it. You
Sir,
submit the week
sir,
8 assignment.
week 8 date will change, sir. You will change the week 8 submission date. It is showing us 8th August, sir, for week 8.
You know, week 8 assignment, 8th August is for the uh, multivariable calculus assignment. Week 9 assignment, which is wrongly uploaded on the week 8. So there are two assignments. If you look at carefully, there are two assignments. First one is week 8, the graded assignment, which deadline of which is 30th of July. Is it clear?
Sir,
Yeah.
sir, there is one another problem that is not the part of today's topic. Actually, I am just asking just general.
Okay.
Sir, my OPP2 exam is clashing with my assistant engineer exam that was actually from state recruitment.
Okay.
So I have mailed support team, but still they are not responding to me till now.
Okay.
So what should I do?
Uh, uh, I don't know. Like, uh, maybe contacting support team is the one that I would also
I
suggest
have
to you.
already mailed IIT Madras, but still they didn't respond me anything. It is first
Yeah.
time they
So
are
I think
responding. Actually, every time whenever I mailed, they always respond me. But
you can send another reminder to them and mention that why it is important to resolve it as soon as possible. Okay.
yes, that is why
So
I'm
that they
just mailed them before 1 month.
yeah. So you send another reminder email to them. Mention that it is important for you to uh, uh, yeah. Just mention all
Yes,
the details. So I think they will respond.
yes,
Okay.
sir.
Thank you
Even
everyone for joining. Yeah. 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 You
even
you
though
were saying something.
I told